So trying to understand the forward process in NOPROP, the forward process, how it is different than forward propagation, because NOPROP, the key advertisement is there is no propagation. The forward process framework is conceptually different from the traditional forward propagation. So let's break down the differences. Okay. Traditional forward propagation purpose to compute the output of the network given an input to store intermediate activations for use during the backward pass. Okay, fair enough. To compute gradients. The forward propagation is represented Z0. ZTFT is a transformation function for layer T parameterized by theta T, and ZT is the activation at layer T. Okay. So for NOPROP, the purpose is to compute the next activation in a stochastic manner, incorporating noise at each step to enable each layer to be trained independently to denoise the noisy target. Okay, but it still depend on previous layer, right? ZT minus 1, ZT equals to ZT minus 1. UT is a residual block parameterized by theta T that takes the previous activation ZT minus 1 and input X, and epsilon is the Gaussian noise. So these are the key differences. Stochastic nature, the typical forward propagation is deterministic, and this one is stochastic process. And more importantly, the layers are trained jointly using backpropagation, where here each layer is trained independently. So it only depends on the previous layer to pass the activations, but it doesn't need to store intermediate activations for and computing gradients for when it happens during backpropagation, because there is no backward pass. And the residual blocks, because for propagation typically uses standard layers with activation fully connected convolutional. Here NOPROP uses blocks that incorporate the input X and only the previous activation, just immediate previous layer to compute the next activation. Noise injection, forward propagation does not involve noise injection. NOPROP does have noise injection, that's an extra thing. Here is an illustrative code example. So the purpose of noise injection, it is doing several things, like for instance regularization. Since we don't have like L1 L2 regularization terms like they have in backpropagation, noise does the trick. Exploration of the solution space, so obviously noise injection allows this exploration. Escape local minima. Robustness to input perturbations. This is particularly useful in applications where input data may be noisy or corrupted. Alright. Basically, to avoid overfitting, each layer is independently known as a noisy target. Adding noise ensures that each layer receives a diverse set of inputs, helping it learn to denoise effectively. So the loss functions for discrete time NOPROP, we have cross entropy loss, KL divergence, and denoising loss. The denoising loss is the measure of the difference between the predicted denoise level and the true level. And loss function for continuous time NOPROP, we have SNR, signal to noise ratios, fast derivative at time t, loss function for flow matching, NOPROP flow matching. So it depends on several things. Most importantly, the predicted vector field. Z1 is the true level embedding, Z0 is the initial noise. So the difference between these two, and then this is subtracted from the predicted vector field and then squared. So there are several components here. Cross entropy, KL divergence, these are standard ones. Then the denoising loss. So the updating of the parameters for each layer is done independently using gradient based optimization like ADAM or SGD. The key difference is each layer is trained independently, and the training process does not require a backward pass.